The next reaction is the addition of primary amines to give imines. That's how this word is pronounced. And they are also known as shift bases. So we call this primary amine, the RNH2, because this nitrogen right here is attached to one other carbon. So this is a primary amine. So you would say if you had a secondary amine, then you would have two carbons attached to this nitrogen atom in the amine. So the product of this is the following, and we will discuss the mechanism on the next page for better understanding. So you have the nitrogen double bonded to that carbonyl, originally carbonyl carbon, plus H2O. Now, of course, you don't have to show the H2O, but this is the main product right here. This is driven with the addition of acid, base, or heat. Typically, you have the acid and the base, mostly the acid. So this is the product, and this is an amine. So it's not imine or something like that. It's called an amine. Now, the idea is very simple. If you have primary amine, all you have to do is basically replace this oxygen with the nitrogen. I'm giving you a very quick shortcut with the nitrogen and whatever is attached to it. That's non-hydrogen. So in this case, notice how I added the N and the CH3. Remove the oxygen. So this applies also, as a quick shortcut, this applies also to any of these. You can add any of these, and you would add, again, the nitrogen, and then whatever is attached to it other than the hydrogens. So if you add hydroxylamine, you would produce something called an oxime. You don't have to know the name, but basically it would look like this. So this is called an oxime. Let me just write it. You don't have to know the name. I'm not asking you to know the name, but I just want to write its name so you would know what this is called. Of course, the other things also would produce, again, the product with whatever attachment. So let's look at the mechanism because that's important. So the mechanism involves two steps. The first step is addition, and the second step is dehydration. So we'll talk about this more in depth. Now, in terms of the mechanism, we're going to look at the acid catalyzed. And we usually need a pH, and we'll explain this pH of around 5. So not a strong acid. So let's look at the mechanism. And again, this applies to whether you have a ketone, whatever is attached here. So we have our carbonyl, the aldehyde, and then we have our primary amine, methylamine. So you need to remember that nitrogen has a lone pair on it. So it's nucleophilic. Remember, a lot of those reactions are reversible. You know now the next step for addition reactions. You see a pattern all the time. So you shouldn't be guessing how the reaction is going to proceed. Many of the steps are really the same. So here we have to show the H's here because we're going to need to deprotonate one of them. So what we have here now is we have nitrogen with 4 bonds. So that means it has a positive charge. So it's very acidic. Very well. So the next step is you have another methylamine standing around. Now, this might be slightly different than what your book gives, because I think, in my opinion, this is a better mechanism, less complicated. So the deprotonation takes place first, and then you would have very well right there. So that's the lone pair that was that. So this protonated amine is acidic. So it's going to protonate the charged oxygen. So it's going to go like that. Go to the N. So again, you would expect these. So let's finally form the product here. So this is our product. And this product, as we mentioned, or we haven't mentioned that, that has a name. It's like an hemiacetal. Remember, in the hemiacetal, you had an OCH3 or an OR. Here you have an N, or the amine portion. So this has a name. This allows me to write it. This is called a carbinolamine. A carbinolamine. This right here. So it's analogous to a hemiacetal. Very well. So that's the addition portion. Now we need to talk about dehydration. Dehydration, which is the removal of water. So the dehydration is we grab what we have from what we ended with. And you know you need to get rid of the OH. Can't leave right now, so it has to be made to leave. So then, now as we explained, we said we're using an acid catalyst and it's best at 5. So it's slightly acidic, not too acidic. And this is why we still have the protonated amine that is going to serve as the donor of the H's, the protons. So we can protonate the OH. So the next step would be very well. So now this is a good leaving group. The water is a good leaving group. So those electrons are going to, let me just redraw this slightly here so we can put the lone pairs above that bond. So what's going to happen is that these electrons are going to come down and then the water leaves. So thus you're creating the double bond for the imine. We need to just adjust the angles here. And there's a positive on that nitrogen. 4 bonds, 4 bonds. So all we need to do now is deprotonate the amine. Still have the methylamine now. And then finally you end up with, and then we're going to redraw it here. So here's your amine. So the special points about the mechanism is that the reaction runs best when run slightly acidic at pH of 5. Why? That's the question. The reason why is because of the following. You're starting with methylamine as a nucleophile. If you use a lower pH, more acidic, so at lower pH than 5, what do you think happens to this? This becomes protonated because it's basic. So it's basic to begin with. So we say NH2, CH3 is significantly protonated. And if it's protonated, then it is no longer a nucleophile. So if this becomes protonated, then this is no longer a nucleophile. So the reaction stops. It drops significantly because, again, you are not able to generate or to use this as a nucleophile like we did here. It doesn't have a lone pair to attack. It's already happy by, right. So again, they're no longer a nucleophile, again, because there's no lone pair. Now you might ask, okay, so what about higher than 5? Well, anything higher than 5, okay, at higher than 5, then pH 5, the leaving group, which is the OH, is not protonated. So meaning the OH minus will not leave. So that's why you have to have it at a pH of 5. That way you ensure that you are able to preserve the nucleophile, the amine nucleophile, so it can attack. And then that at the pH of 5 as well is able to serve as a protonated amine later on so that it can help the leaving group become OH. The OH become water and leave readily. So that's the idea here, is you need to balance this. If it's too high of a pH, then you will be stuck with the analogous of the hemiacetal, the carbinolamine. So, and if it's lower than 5, then you will be stuck with pretty much what you started with. You won't have, maybe you'll have a protonated aldehyde or ketone, but that's about it. So that's why you have to balance it at that pH.